Hello guys, welcome back to the YouTube channel of The Concept Guy, and in this video we will talk about Euler's method and how we can actually perform this method in MATLAB 2. So first of all, why this method? So it is a method for numerical integration in which we will actually find the next point. Like if we have the initial point say y0 and x0 and we need to find the next point, that is say y1, so we can find it easily with this method. Okay, so what is the basic approach of this method is that Euler considers the slope. Okay, as simple as it. Euler's slope. So what does this slope really mean? So here what we can see is that our curve is quite ups and downs in these curves. So what we can do is divide these sections in various parts and find, like say from x0 to x1 we have a step size of h. So like x1 minus x0 is h. So in this h part, okay, in this part what we can see, there is almost a particular slope, okay, an approximate almost slope. So slope here we can define it as y1 minus y0, this minus this minus this, and x1, because y1 corresponds to x1, so what we'll do is x1 minus x0, y1 minus y0 and x1 minus x0. So this is my slope, and this slope is a function. So f of it is a function of x and y. Okay, so this is my function, and this could be any function, but what we have at last, that this is the slope, the tangent, okay, the approximate tangent that we will discuss here. So what we have to do is, we know x1 minus x0 is equal to h. Let's put it out. So after putting that, we have h into f of x comma y. Okay, so this is what we get as finally y1 is y0 plus h into f of x comma y. So Euler is nothing but slope. Okay, but this slope function here, you see f of xy, it is just an approximate slope. So what we need here is that our h to be so small that this approximate slopes becomes almost the exact slope. Okay, so for what we can do is we need to modify. Yes, we need to modify our Euler a bit. Okay, so first thing, we got the information from here, and let's say the easiest reduction to get a particular exact value here is that we divide this h interval in such a way that this slope and this slope are almost equal. Okay, so our first dividing of this whole area of x0 to x1. So first division and the easiest division is that I divide it in a half. So here it is my h by 2 and this is h by 2. Now I have divided it half. So you might ask a question that why modify Euler? Why modify Euler? So a case to be told here is that if we look from Taylor's, so y of x, so let's say xn plus 1, okay, so y of xn plus 1 is y of xn plus, so this is my function, and it is plus h into y prime xn plus h by 2, h square by 2. Okay, so this is 2 factorial actually, and y double prime xn and so on. So we have terms till this part, as we see. Okay, so we have terms till this part, but all these terms are actually neglected in this Euler's method. So we need to consider them in the modified Euler's. So the easiest and the most easiest approach is that, okay, so the best approach is that we divide the step size h into h by 2 equal parts, this part and this part, okay, and get their f of x, f of xy different functions. So let's say first is f1 and second is f2. So what we find here is that I have two slopes now. Okay, so for first part we will have a different y, say y1, and this be y1 prime. So my first part is y1 minus y0 by again, but this size is h by 2. So we will take h by 2 is equal to f of f1 of x comma y, and in this x comma y we will put the value, the initial values, because we know the initial values only. Okay, so using this and the next part, we can ultimately get that my y1 prime is equal to nothing but the y0 plus h by 2 times of f of 1 x0 comma y0 plus f of 2 x comma y. And this is the final Euler's method, the modified Euler's formula. So it's nothing but dividing and getting the slope. So our slope is really important, which will be given in questions. And we know the initial values, say y at x is equal to 0 is 1. So these kind of initial values are generally available with us. Like y is 1 when x is 0. So let's now see what happens in MATLAB. So guys, let's now just try this method in MATLAB. And so we have a question here. So f of x comma y is it's given as minus x into y, and the initial points y0 is equal to 1 and x0 is equal to 0 are given to us, and h is the step size, and we will keep the h as 1, and we want the curve till x is equal to 10. So here it is in MATLAB, and we are in the command window. We will write edit my Euler. Okay, so we will go to the editor window and make a my Euler space, where we will just specify the x0 and y0 first. Okay, so let's write x0 is just a way, let's write x0 first. X0, yes, here it is. X0 is 0 and y0 is equal to 1. Okay, next we see in the question that we have a step size of h is equal to 1. Okay, so let's specify that. Okay, these are the things that we know, and our last ending point is x last, say. So x last is the variable that is 10. Okay, the last point of x. So we need to plot this using the Euler's method. Euler's method, as I have already said, that it has the initial points and the approximate slope, and both are given in the question. We need the n. The n is the number of steps in which this thing will actually work, the method will actually work. So x last minus x naught, this is the whole space, and we divide it with the step size h, so we get how many spaces. Okay, so how many areas we need to actually look at in the method. So let's just make the vectors first. Okay, and we can change the vectors accordingly later on. So we have two variables here, the x and the y, and let's capital X denote the vector, the column vector. So we will start from x naught and x naught plus h, x naught plus 2h, kind of that. So we use the colon operator to add h again and again and till the x last point. So we need a column vector here, so we put it the transpose. Next we have capital Y here. Okay, we don't know what is it is. We are going to calculate it with Euler. So let's just say it is a 0 vector. So zeros n plus 1 comma 1. So why n plus 1? Because the last element will actually also, the x last will also give a further x n plus 1 term. Okay, so all are 0 initially, but here one thing you will notice that y1, the first element, is known to us, the initial points are known to us, and that is y0. Okay, y0 here is 1, so we have the initial, the first element of this column vector of y. Okay, capital Y. Next we need to find different y's corresponding to different x using the Euler's method. So the main method here, because there are so many y's and x, let's try looping, and we will use a for loop for this. So I is the loop counter, and it will start from 1 because we want the first element, use the first element of y to get the next element of y. So 1 to n. Okay, so we have 1. Okay, and this is our f function minus x into y. We will put that, and f is, as we have discussed, it is a slope. Okay, so slope is very important. F is equal to minus x into y, that's the function, and y, the capital Y, next element, so I plus 1, the next element we want. Okay, that should be equal to y, yi, the previous element. Okay, if I is 1, yi is y naught, plus h times f of f. Okay, f, here we need to put x and y capital here and put their counters too. So let's just change it, as this is not x but the capital X and the ith element, and that is also not y but capital Y, ith element, that we know, because I will first start with from 1 and next we want y2 here, and so on. So let's end the loop and let's plot the results. So easy function, we will use a function plot, that's a MATLAB inbuilt function, plot and x comma y, x in the x-axis and y in the y-axis. Here we have the curve. Okay, so let's just save it and let's run it. Okay, let's wait for some time. Yes, here is the plot. So as you see, this plot is quite direct, like it's quite strict. Okay, it's not a curve, and it ends at 2 in the x-axis. Okay, so let's try a different step size, because as we know the step size reduces, we are actually getting a better approximate. So we reduce by factor of 10. So now you see it's not a straight line type curve, it's a just rounded curve. Let's decrease the step size further, and it's almost more rounded. And after that, I think for 0.001 step size, it's almost the same. So hope you like the video. Please try different step size and with modified Euler also in MATLAB, and do tell us what the results is. And finally, we have seen that Euler method is very simple method. We will also discuss RK method in the further videos, and you can actually plot